Welcome to the British Geological Survey lecture, Chasing Carbon, an Onshore and Offshore Challenge. My name is Maxine Akhurst. I'm a geologist at the BGS, the British Geological Survey. Today, 4 scientists from BGS will present their work to reduce carbon dioxide emissions from heating, industry and power generation. We will outline our research on the rocks beneath our feet and surrounding seas to provide geoscience solutions that can contribute to the transition to net zero emissions for the UK. Our research aligns with both the aims of the government's Energy White Paper, Powering Our Net Zero Future, and the key themes of COP26, which is only a month away. Firstly, Dr. Corinna Abesser, a hydrogeologist who leads investigation of geothermal heat in BGS and is currently seconded to the Parliamentary Office for Science and Technology. Corinna will outline the role of geothermal energy in the decarbonisation of heat. Dr. Alison Monaghan, science lead for the Glasgow Mine Water Geothermal Observatory, will then show us how underground observatories support cost reduction and de-risking of geothermal heat. I am the third speaker. I lead research investigations of rocks deep in the subsurface to permanently store carbon dioxide. Today, I will summarise how geological storage of CO2 can play a role in the energy transition. Our fourth speaker is Gareth Carter. Gareth is a marine geoscientist. His research interests include how geology constrains offshore infrastructure, and he will describe how our glacial past is so important for offshore wind energy. There will be time at the end of the presentations for us to respond to your questions, so please use the Q&A facility to ask us. Our first speaker is Dr. Corinna Abesser.
Thank you, Max. So my name is Corinna Abesser. I lead geothermal energy research at the British Geological Survey. And I'm going to talk to you about the role of geothermal energy in the decarbonisation of heat. Now, my controls, why have I chosen that topic? And the reason being is that the UK still faces a large challenge in the decarbonisation of heat. Heating remains one of the biggest sources of carbon emissions in the UK. 85% of our homes are still using natural gas. 20,000 homes would need to be converted to low carbon heating to meet our 2050 net zero targets. And there is no silver bullet that can achieve this target. So we need to use a combination of low energy technologies when and where they are available. So geothermal energy is such a low carbon option that we can use for heating. It is a mature technology that is available now, and it is available in all parts of the UK. Now, what is geothermal energy? Geothermal energy is all energy that is stored in the form of heat beneath the surface of the solid Earth. It originates from 2 main sources: the decay of natural radioactive elements within the Earth's crust, as well as from primordial heat, which is left from when the Earth was formed. The energy is stored in rocks and soils in the form of heat. The benefits of geothermal energy are that the heat is constantly replenished, so it's a renewable resource. It's independent of the weather, so it can provide constant supply, irrespective of whether there's sun or wind. And it is exploitable by different technologies, and so that makes it very scalable, as I will come back to later in my presentation. There's different technologies by which geothermal energy can be extracted. Here you see a slide with a shallow and a slide that shows sort of the distinctions between shallow and deep geothermal. And just to point out that the terminology is very confusing because it doesn't actually relate to the depth of the system, but to the system temperature and whether the technologies use ground source heat pumps or heat pumps. On the left, you see the shallow geothermal systems, and they include open loop ground source heat pumps, closed loop ground source heat pumps, and mine water energy systems. These systems extract heat from water and ground at ambient temperatures of about 10 to 20 degrees and upgrade this heat using a heat pump. And so they're upgraded to the temperatures that we need for heating, so 40, 50, 60 degrees. On the right-hand side, you see deep geothermal technologies. These tend to not require heat pumps, abstracting water at temperatures of 60 to 70 degrees, which can feed directly into the heating systems, including district heating. In some places, we also have heat sources that are hot enough for power generation. Now, depending on the temperature, geothermal energy can be used for different applications. And here are some examples ranging from snow melting, space heating, industrial processes to power generation, as I already mentioned. You can see here that space heating occupies a wide temperature range from less than 20 degrees to over 100 degrees. And this means that the geothermal system can provide space heating across a range of different scales. At the lower end of the scales, we have heat pumps, geothermal heat pumps, which can supply individual homes or smaller ambient heat networks for a few tens of homes. Scaling up from that are mine water systems, which can supply low temperature heat networks for a few hundreds of homes. And the deep aquifers, so the direct use applications, they can supply direct heat to district heating networks of 100 to a few thousands of homes. Now, you might want to, you might ask yourself, can we find geothermal energy in the UK? And the answer is absolutely. On the left here, you see a plot of the ground temperatures of the UK at 100-meter depths. And this is here to illustrate that heat is available all across the country. And this would be heat that can be exploited by geothermal heat pumps. So geothermal energy really exists everywhere in the UK. There are other systems here on the right-hand side, like mine water geothermal. These systems exist in many parts of the UK in the vicinity of big cities. And the great thing about them is they store a huge amount of heat within the water that they contain. And as I said, because they're so near many of the cities of the UK, there's a direct link between the supply and the demand. We also have different deep geothermal targets in the UK. The drilling costs for these are higher, but they can also provide considerably more heat. And they don't require a heat pump. So the estimated resource in the deep aquifer systems, which are marked here in sort of yellow, blue, and green, are such that we think they can provide sufficient heating for more than 15 million homes for 300 years. So how are we currently using the resource? Here are a few numbers. And if you look, we sort of just under 39,000 ground source heat pumps, more than 6 mine geothermal systems, 2 power generation systems in development, and 1 direct use heating system, which has been operational since the 1980s. However, if you compare this with Europe, you can see here that the UK is using the geothermal resources much less than neighboring countries like France, Germany, the Netherlands, which have similar geological settings to the UK. The difference and the experience in these countries is that the success of geothermal development is closely linked to government support, government commitment in the form of policies, regulations, and incentives. This is very important for geothermal energy, which is a nascent industry. And we actually have an example in the UK of how important government support is for new industries, because offshore wind has demonstrated this very well. Gareth will talk about this later in his talk, but I just want to remind you that 20 years ago, wind farms faced very similar problems to geothermal, in that high capital and operational costs made it very unattractive and risky for investors to get involved without any government backing. Now, the government, recognizing the potential for renewable energy generation from wind, committed to supporting this industry and provided sort of long-term policies and funding for the supply chain, for innovation, finance, and skills. The commitment and support from government sort of send the message or signal to industry that this technology has government backing. And so manufacturing base moved to the UK, jobs were generated, deprived areas rejuvenated, and the UK is now a world market leader for offshore wind. I believe that a similar journey is possible for geothermal. And so our proposal to policymakers is to commit to developing this resource and clearly defining government targets and policies of how geothermal energy will be progressed in the UK. And as an example, what such a target could look like is here's what Arup sort of proposed as a short-term target of 12 geothermal heat projects in the next 5 years. And the benefits of that would be provision of low carbon heating to 500,000 homes and carbon savings of 100,000 tons a year. So in summary, the key message from my presentation here is that geothermal energy is a low carbon resource for heating, which is available now all across the UK and at all times. The resource is sufficient to provide heating for more than 15 million homes for 300 years. And, but it requires policy support and investment to realize this potential, similar to what we've seen for offshore wind. But with the right policies, geothermal energy could make a considerable contribution to the decarbonisation of heat in the UK. And with that, I'm passing on to Dr. Alison Monaghan for a lecture on underground observatories. Thank you very much.
Thank you, Corinna. I'm going to share my screen. Okay. So yeah, just to give a bit of background, I'm a geologist, and for the last 5 years, I've been involved in developing an underground observatory, which gives us an unprecedented look into the subsurface in space and time. So linking back to Corinna's talk about geothermal energy, she's shown that geothermal technology is approved and that there are extensive potential across the UK. There are great benefits to geothermal energy, but there's also some challenges such as the capital costs, technical risks, and as just discussed, policy and regulation. So I want to explore a bit more the question of how do we scale up to widespread deployment of geothermal energy? How does it become economically viable? Is it sustainable? And what about environmental impacts? So to answer some of those questions, a part of the jigsaw is something that we've been working on at the Geological Survey, and these are underground observatories as mentioned in the title. So at this slide, the top of this slide shows some of the rationale really for underground observatories. So if we can increase the evidence base around geothermal energy and so on with real world data through time, if we've got places where we can test techniques, we can develop processes, and we can test new technologies, then together those things will help us to reduce the risks of those technologies, to reduce the cost uncertainties. There are also places where we can bring people to show that the technologies work and that what the risks are and any environmental impacts and what they are. And the observatories themselves are things that are flexible and are at scale. They're pieces of research infrastructure. So what I'm describing are the UK geoenergy observatories, which BGS has delivered on behalf of the UK government. It's a major investment by UK government for world-class science, looking at clean energy at the scale we need to deliver it by 2050. And going back to the slide that Corinna used, looking at shallow geothermal energy, this is the same image, looking at the underground really down to about 800 meters. We've developed in the Geological Survey 3 observatories, so 3 at-scale facilities. So one of these is looking at the shallow geothermal energy ground source heat potential in Cardiff, the Cardiff Urban Geo Observatory, looking at shallow ground source heat. In Cheshire, an observatory is planned, looking at aquifer, geothermal, and energy storage, heat storage, as well as other clean energy technologies. What I'm mostly going to talk about today is the Glasgow Observatory, which has been developed to look at mine water heat and also thermal storage in mines. So the Glasgow Observatory on this map is located in the eastern side of Glasgow, the east end of Glasgow, close to the River Clyde. And it's about 6 kilometres from the COP26 venue, which is on the western side of the city centre of Glasgow. So this is an air photograph of the location of the observatory in Glasgow. And so you can very clearly see the River Clyde running through the slide in a big meander. And the city centre of Glasgow is off towards the top of this image. So the observatory is a set of boreholes and research compounds, and these are the dots that are on this image. This is where we've drilled boreholes, in this case into the mine workings. The green dots are boreholes that have been drilled into the mine workings at about 50 to 90 metres below the surface. And it's those mine workings that contain the warm water from which we can pump to the surface and extract the heat energy. The purple dots on this image are environmental monitoring boreholes, so we can monitor the impacts and also the ongoing environmental change in this area. So altogether, there are 12 boreholes, mainly spread across this site at Cunningar Loop in the east end of Glasgow, and also a seismic monitoring borehole, a deeper borehole over a little bit farther west. And what's really important about this observatory is it's in a real world setting. It's in an urban area of regeneration that's typical of many of our towns and cities and faces similar challenges to those towns and cities across the UK. So it's representative as a location. So just a little bit more about what the observatory is. So I've mentioned on the top left-hand side of this image, it's 12 boreholes and 4 research compounds. There's some pictures there of some of the rock core on one of the research compounds. The boreholes that have been drilled are not ordinary boreholes. They have an awful lot of sensors down the outside of them for sensing temperature and geophysical properties of the subsurface. They're places to do a lot of sampling and a lot of monitoring. Part of the observatory has also been engaging with the public and with stakeholders to raise awareness of what's happening. We've conducted a major programme of environmental baseline monitoring, so to understand what the environmental change is before any geoenergy technologies are trialled at the site. So across the water, the gas and the ground motion type spectrum. And one key thing about the observatories is that all the data that's produced as the baseline data set from the Geological Survey is open data. So all the data is available on a website, and there's a lot of data from Glasgow already available on that website. So just looking in a little bit more detail, just to explain what is at the observatory, this is a block image of the underground, and you can see the ground surface in green on top. And down in the image, you can see where the mined coal seams are, and then the grey lines going down into them are the boreholes that have been drilled. And just to kind of give a visual impression of what the boreholes are doing, they're sensing the underground and they're sending out signals. They're sending us back signals on the temperature, the physical properties of the underground, the water level, how the water's flowing, and so on. And what we're actually involved in at the moment is putting the final pieces of infrastructure, the geothermal infrastructure, in place, and that should be there by early 2022. And that will enable us to make geothermal activities kind of happen and make subsurface changes in heat happen in the subsurface to be able to study those. So I just wanted to give a quick example of how that might apply to increase the evidence base around geothermal and de-risk what we're trying to do, or better understand what happens in geothermal systems and reduce cost. So some of the key questions that people ask is, how much heat is down there? How much geothermal heat? And is it sustainable? Will it carry on for a long time? So we're looking at the subsurface resource and its operational sustainability. And so what we've got at the Glasgow Observatory are boreholes that go down in through coal mine workings, which are shown at 2 levels on this diagram. And we can imagine a piece of research or development where people will come and they will pump water out of the mine working to take the heat out of that water. And then they'll monitor a response in the mine working adjacent to that. And that will tell scientists how much heat is available, how long it might last for. It's a very simplistic example, but it's an example of how such an infrastructure might be used to answer a research question. On the right-hand side of this slide is an example of some of the monitoring data that also helps to answer that question. So this is an image, a plot of the temperature down a borehole. So you can see that the temperature increases down the image, down to a temperature of about 11.5 to 12 degrees at about 50 meters below the ground surface. And the sensors within the borehole are monitoring that through time. So we can really start to see temperature variations within the subsurface and with geothermal activities. The observatory is also a place where scientists and engineers and so on can come to test technologies and processes. And it's a real place to come and do this. It's at scale, it's complicated, but it gives people the flexibility to do that kind of research. So people might want to come and develop sensors, other technologies, or do analytics on the time series data to look at the digital environment, the environmental responses to some of the changes that are happening under the ground. So just to summarize those last few slides, I guess what I'm trying to show in this presentation is that the observatories, the underground observatories, are places where there is infrastructure, there's boreholes, there's monitoring and so on. And that really increases our evidence base, our data. And then we can use that data to answer science questions, research questions about how much resource there is, what the environmental impacts are, how long the operational lifetimes and de-risking aspects of those operations. And then those are kind of the science questions, and those questions then influences the wider sphere of the economics, the licensing and regulation and policy and so on. So that's the aim with this infrastructure. So just to summarize and finish off this presentation, we've seen through hopefully both myself and Corinna that geothermal and thermal storage can also contribute to the decarbonisation of heat. They can be part of that decarbonisation of heat for our buildings. To roll out widespread deployment across the UK, there are different pieces of the puzzle. Corinna talked about the importance of policy and regulation. I've given some examples about the technical aspects of increasing the evidence base, of a place to look at processes and technologies to try and make them more cost effective. And that's one part. So there's lots of different parts that need to come together. But these underground observatories, really understanding what's happening in the subsurface through time when we use it for shallow geoenergy purposes is really important as we go forward. These observatories are open for the academic and the commercial research and innovation community to use, and there is a lot more information on the website. So thank you very much for listening today. Again, I'm very happy to take questions. Please post them in the question and answer session, and I shall now hand back to Maxine. So thank you very much.
Hello everyone. My name is Maxine Akhurst. I'm a geologist at the British Geological Survey, and since 2008 my work has been focused on how natural UK geological storage resources can be used to help us reduce our national carbon dioxide emissions. Today we'll consider how UK geology can contribute to a decarbonising industry, power and hydrogen production with carbon capture and storage. We will very briefly review the UK government's net zero emissions policy, and this includes how carbon capture and storage, or CCS, can help us permanently reduce industrial emissions, and also the large-scale production of hydrogen with CCS for commercial and domestic heating. We will look at the UK's geological carbon dioxide storage resource. Then BGS research to assess the UK storage capacity needed for industrial decarbonisation, and the modelling of first and next sites for permanent storage of UK CO2. Let's look at the UK government's strategy for decarbonisation of industry. Firstly, the Energy White Paper, Powering Our Net Zero Future, which was published in December 2020. The strategy for decarbonisation of the UK industry is currently focused on clusters, places where there are many large point sources emitting carbon dioxide. Around half of the emissions from manufacturing and refining are concentrated in the 6 clusters shown in this map here. The annual carbon dioxide emissions are measured in millions of tonnes of CO2, and these range from 3.2 million tonnes for Southampton to 10 million tonnes for Humberside, with the total annual emissions from these 6 clusters of 35 million tonnes per year. The close association of many sources will enable effective implementation of decarbonisation technologies and also economies of scale to reduce the cost per tonne of CO2 stored. The UK ambition is in the Energy White Paper, and it is to deliver 4 low carbon clusters by 2040, 2 by the mid-2020s and another 2 by 2030, with at least 1 on power generation. Greater ambition is for 1 or more fully net zero clusters by 2040. So we are already in 2021. How will this be achieved? Plans have been submitted for industrial decarbonisation in 6 UK regions, and all are listed here. These include the Acorn CCS project in Scotland, the Net Zero Teesside and HyNet projects in Northern England, and these 3 all plan to start operation in the 2020s. Secondly, let's look at the Prime Minister's 10-point plan. This illustration summarises the 10-point plan for a green industrial revolution. Geology is included in 6 of these areas, highlighted by these circles. We have already reviewed geothermal heating for greener buildings with Corinna and Alison. We will also hear today about offshore wind power. From my own research interests, capture and permanent geological storage of carbon dioxide is included on 2 of these 6 areas. Carbon capture, utilisation and storage, of course, but also under large-scale production of hydrogen. Zooming into these 2 points. The UK plans to reduce emissions from industrial processes where carbon dioxide is a byproduct, and power generation by fuel combustion using capture and permanent geological storage of carbon dioxide. The UK also plans to reduce carbon dioxide from domestic and commercial heating by switching supply from natural gas to hydrogen, which produces only water at point of combustion. Large-scale production of hydrogen, sufficient for commercial heating and domestic heating of large urban areas, is by reformation of methane at industrial sites with byproduct carbon dioxide. So large-scale industrial hydrogen production also requires CCS for emissions reduction. The UK ambition is to store 10 million tonnes a year by 2030, as shown in this slide, and that is equal to the emission of 4 million cars per year. This sounds good to decarbonise the gas in our boilers and cookers and used to drive the manufacture of the items that we use. So, do we have enough geological storage capacity for the required millions of tonnes of CO2 to achieve UK emissions reduction? BGS role is the national provider of UK geoscience information. BGS hosts the UK National CO2 Storage Database, CO2 Stored. The database contains data on more than 570 prospective sites offshore around the UK. The sites are shown here by the geographical position of the open circles. The type of store and capacity are indicated by the colour and size of circle, respectively. The stores are depleted hydrocarbon fields and saltwater sandstones. The database provides much detailed information on each, including calculations of theoretical storage capacity. and the database has been the starting point for industry CO2 storage projects. So what does it tell us? First of all, that we do have sufficient storage capacity. The summed UK theoretical storage capacity is 78,000 million tonnes of CO2, that is 78 gigatons. It occurs predominantly within saltwater sandstones, termed saline aquifers, and the total significantly exceeds UK ambition to store 10 million tonnes per year, also the total from all 6 clusters of 35 million tonnes per year. Recent BGS research considers where and how the CO2 can be permanently stored. Before we review the BGS research, we should also be aware that 2 offshore CO2 storage sites have been in operation for more than 2 decades by our near neighbours, Norway. The Sleipner CO2 injection project, shown here by the green circle, has been storing 1 million tonnes of CO2 per year since 1996, so a total of 25 million tonnes of carbon dioxide, and is a tried and tested technology. To investigate the where and how, BGS considered the plans for CO2 capture for storage at 2 industrial clusters, Grangemouth in Scotland and Teesside in England. We reviewed published industry plans and concepts in the Elegancy project. We compiled, summed and plotted the values for supply to 2055. And after 2055, the anticipated supply was plotted at a constant rate or at plus or minus 10%. So what did we find? For initial CCS projects, with planned capture from industry processes and power generation, the curve is shown in blue. Capture and storage rates are less than 3 million tonnes per year, so very readily accommodated within our storage capacity, but will not meet the government target of 10 million tonnes a year by 2030. Using industry plans for capture at a greater number of industrial CO2 sources at the 2 clusters, plus large-scale hydrogen reformation with CCS, the growing projects curve is shown in brown. There is a marked increase in supply of CO2 for storage with the addition of planned hydrogen reformation. Notice the y-axis change in scale. The rate of supply increases to 23 million tonnes per year in 2035. The government target of 10 million tonnes per year by 2030, shown here in purple, is exceeded. For mature projects in the green curve, industry plans assume high rates of CCS deployment within and beyond the region, import of CO2 for storage, also widespread large-scale uptake of hydrogen for domestic and commercial heating. The rate of annual capture increases to around 57 million tonnes per year by 2045. And again, the government ambition for 10 million tonnes per year, as shown in purple, by 2030 is exceeded. These are very exciting project results. The supply profiles inform the storage research in the Align CCUS project to investigate feasible sites to store the CO2 from Grangemouth and Teesside. The Align project used the CO2 stored database to select feasible sites for each of the Grangemouth and Teesside industrial clusters. The sites should provide adequate total storage capacity for the period of injection. They should be able to receive the CO2, the injectivity, at a rate sufficient to meet the supply. The sites should be within relatively close proximity to the industrial cluster, already characterised to a suitably high level for planned early operation, and should build on existing geological models and appraisal. The sites should be suitable to be included in a storage network, and that network should have the potential for future expansion. Sites were selected and models as shown here. 4 sites for Grangemouth with black outlines in the top map, and 5 sites for Teesside within the black outline on the bottom map. Capacity and injectivity were tested by geological modelling and simulation of storage operations for Grangemouth and Teesside. First sites were assumed to be as planned by industry projects. Align CCUS research modelled the next sites for a growing and mature UK CO2 storage industry from present day to 2100. Storage sites for both industry clusters were modelled for the growth and mature supply curves. Storage at both clusters for the two supply curves was found to be technically feasible. At more than one storage site within a single connected formation for Teesside, as the lower image, and by multi-site storage within one or more storage formations for Grangemouth. BGS research findings emphasise the importance of the need to understand the character of the site boundaries and the pressure response within the formation to the injection of CO2. And there is careful management of formation pressure within a site. Before moving on to my summary slide, I'd like to look again at the CO2 supply for Grangemouth and Teesside, in particular, the growing projects curve and the mature projects curve in brown and green respectively. Maximum storage rates achieved are 23 and 57 million tonnes per year respectively. After 2050, the CO2 supply for storage starts to decline. This is not because we will cease to need the hydrogen for heating. Industry experts expect hydrogen production by reformation to reduce and instead be increasingly produced by electrolysis. That is, using excess electricity from renewables, such as wind turbines, to produce hydrogen. Gareth Carter, who is our next speaker, will tell us more about the relevance of geology to offshore wind-powered electricity generation. So in summary, the UK has ambitious plans to reduce emissions from industry and also domestic and commercial heating by CCS. The UK also has a very significant resource to store thousands of millions of tonnes of CO2. Industry plans to decarbonise domestic and commercial heating using hydrogen will significantly increase the requirement for CO2 storage. The good news is that the UK has geological capacity sufficient to store tens of millions of tonnes of CO2 per year. And our supply curves show that industrial processes that generate CO2 will continue to need CCS to reduce emissions beyond our use of fossil fuel. Finally, I'd like to acknowledge funding from the UK government, BEIS, and the European Commission for the Elegancy and Aligned Projects research. I'd like to thank you for your attention. Please use the Q&A facility to ask your questions and indicate from which speaker you would seek a response. Our next speaker is Gareth Carter. He will outline how geology constrains offshore infrastructure and why our glacial past is so important for offshore wind energy.
Okay, thank you, Maxine. That's great. I'll share screen now. Just that a little bit out of the way. Okay, yeah, so thanks. My colleagues have given some really insightful thoughts on current and emerging technologies, and I will now detail BGS involvement in offshore wind specifically, which is fast becoming a well-established source of green energy in the UK energy portfolio. So my name is Gareth Carter. I'm a marine geoscientist with the British Geological Survey, part of a fantastic team of marine geologists and geophysicists working on offshore renewable energy infrastructure projects, particularly across the UK continental shelf. I've been with the BGS since 2013 and have a variety of interests in the marine geoscience field. However, my main interests focus on geological constraints, challenges and hazards to offshore infrastructure. Okay, shift this out of the way a little bit. There we go. So yeah, the talk will be divided into two essentially. The first part, we'll take a look back at how the cost of generating energy from offshore wind has come down over time. Corinna already touched on this, so we'll delve a little bit deeper. I lean very heavily on the Carbon Trust 2020 report for this, and I make no apologies for that. First of all, it's an incredibly detailed report. I'd recommend anyone to read it who's interested in how the levelized cost of energy has come down for offshore wind. But also I'm a humble geologist and not an economist, so I don't want to get it wrong. So I've plucked quotations and relevant figures from that report for that section. And then we'll go on to look at the role that BGS has played in these offshore renewable infrastructure projects, and more specifically, why understanding ice sheets actually can help to reduce the cost of offshore wind energy productions, which perhaps seems like a far stretch to make, but I'll hopefully convince you otherwise. So I'll try not to use too much jargon, but levelized cost of energy is an important metric for which the offshore wind sector is often measured. So it considers all key costs associated with installing and operating your offshore wind farm as a ratio against the electricity it's likely to generate across its lifetime. So essentially and basically, it's the costs associated with constructing, operating and maintaining your offshore wind farm offset against the average revenue per unit of electricity generated. And this is the effects of the levelized cost of energy over time, which hopefully you'll agree is an incredibly positive chart here. So you can see that in the last decade, really, we've reduced the cost of energy on the y-axis by about a third. And in the UK conditions, this is making it really cost effective or competitive with new fossil fuel generation. If electricity prices return to pre-COVID levels, the government would no longer be subsidising new offshore wind. In fact, the Treasury would be earning revenue instead, which is incredibly positive for the UK economy as a whole. And I think this also nicely illustrates Corinna's point that when we all pull in the same direction, and when there's financial backing and support provided to particularly like emerging and fledgling technologies, we really can turn that into an asset that will make a profit for the economy as a total. So I think this is incredibly positive. The Offshore Wind Cost Reduction Task Force back in 2012 set a target of £100 per megawatt hour by 2020. But as you can see in this chart, when you look at 2023, so the sites that are due to come online in the next few years, it's predicted that the cost will actually be much closer to £40 per megawatt hour, which is a really big success story. So drivers of cost reduction, well, the Carbon Trust identify a few, but the main one is economy of scale. So the increase in turbine size has had been the far greatest the impact on the cost of reduction. So the industry is now preparing for a further scale up from the 8 megawatt turbines up to 12 megawatt turbines, which is set to account for 50% of that predicted reduction in the levelized cost of energy in the coming years. A good example of this is Scrooby Sands, which was commissioned in 2014, and that uses 2 megawatt turbines. So installing a 60 megawatt capacity from 2 megawatt turbines requires 30 individual monopiles and turbine installations. That of course means increased ship time for installation, which is all very expensive, and potentially more downtime in operation and maintenance. Dogger Bank A, which is a round 3 site and due to come online in the next few years, will use the new 12 megawatt turbines. So for direct comparison, installing 60 megawatt capacity requires only 5 installations, which again has many benefits. And as I touched on, this could potentially reduce overall downtime for operations and maintenance. The next slide basically just shows a graph representation of this. You can see for the last decade, or sorry, not for the last decade, but for the decade of 2004 to 2014, the size of turbines mainly fluctuated between 2 to 4 megawatt, and then it starts to shoot up. And you can see an exponential growth, which is fantastic and is predicted to continue to grow over the years to come. So, of course, a very relevant question is, why is a geologist talking to me about economics, and what's this got to do with the seabed and subseabed geology? Well, the simple link is foundations. That's where we come in, and that's where our involvement has been. In 2010, foundation costs, I mean, they are a huge part of the project, and they were in the region of £700,000 per megawatt. This now is in the region of 280 to 350 pounds per megawatt, and that depends on how deep you're driving your foundations. And of course, quite rightly, I think, and understandably, early foundations tended to be over-engineered and conservative. So optimized designs now use significantly less steel, for instance, reducing material costs. And it was also found that we didn't need to be driving them as far into the seabed as initially thought, which means, again, less material, less costs. To date, over 80% of offshore wind turbines use monopiles, and jackets account for a further 15%, followed by gravity base making up a bit more of the remainder. Jackets become cost competitive when used in deeper waters, so maybe 45 to 60 meter water depths, and also where seabed and subsurface conditions are particularly variable and complex. Those that are in the sector will know from the recent round 4 auction and also the ScotWind auction up north of the border that we are now moving into new territory really for offshore wind in terms of water depths, and we're moving away from the safe ground that we're very used to of shallower water depths and into these 45 plus meter water depths. So jackets will play a role there, but then of course we're going 60 meter plus in some cases, and so we'll be looking to quite an exciting new venture of floating wind technology, which reaches commercial deployment in the coming years. So final point about this really is the drivers of cost reduction. Well, we have obviously talked about economy of scale, that's the big driver, but an interesting one as well for, identified by the Carbon Trust was learn by doing. And this basically is learning on the job. And it's a really important aspect to the projects, because as we learn from projects and being part of geo teams with different disciplines from different organizations from both the private and research sector, we're able to take that knowledge into the next generation of offshore wind farms. And so that knowledge comes with us, not just about the seabed geology, but also how that impacts on foundation design. And it also encourages collaboration through the supply chain between the private sector and research institutes. And this is where BGS's knowledge of the seafloor and subsurface is able to feed into foundation design. So this quote is taken from Charles Lyell, who's a famous geologist. If you're a geologist and you don't know who he is, then shame on you. He was the author of Principles of Geology, and he introduced coined this phrase, the present is the key to the past. So I think this is a good point where going forward in the presentation, we can take a look at present day glaciated landscapes and landforms and processes. We can begin to appreciate some of the complex geology upon which some of these offshore wind farms are being sited, say in the North Sea, for instance. So here we can see a glacier in Iceland. A colleague kindly donated me this photo. I'm not going to try and pronounce the name of the glacier because I'll get it horribly wrong. But in this example, we can see that the glacier terminates in a large proglacial lake. So we can expect to encounter lake sediments, which might be nicely varved or rhythmically laminated silts and clays. But then we can also perhaps encounter contorted and folded beds or associated with slump deposits as more sediment has been introduced to the system. And as that ice sheet retreats or the glacier retreats, you may get meltwater pulses. So you may have sediment gravity flows too, giving you, say, like a thicker sandier deposit. And there might be thick wedges of sand associated with fans deposited around a margin of the lake. So you can think even within this one environment, the lake environment alone, you have multiple different depositional settings or soil types that we might encounter. To the right of the image, we can also see that the lake is roughly constrained by a topographic ridge or a high that runs across there. And that's a moraine, and that will be pushed up generally. In this example, would have been pushed up by the front of the glacier as it went forward. So it will be almost like a bulldozer effect, I guess. So that will be, as you can imagine, a horrible mess of different soil types, different producing very variable and different ground conditions. So you may have, say, majority being clay to silt size and some sand in there, but then you may also go right up to individual boulders and clusters of boulders and cobbles, which can, of course, have challenges for pile driving, for instance. You know, presence of boulders can cause damage to the pile tip or indeed pile refusal altogether, which all costs downtime, and it's all negative impact on the overall cost to the project. You can see further to the right here that the lake is drained through a river network system, so these glacial fluvial river channels. And again, these create highly variable ground conditions over small lateral distances. So I'm sure you can imagine that either side of that lake, river channel, will perhaps have very different ground conditions to the channel itself. The channel may be infilled over time with cobbles, gravels, and sands. whereas the surrounding area, for instance, may be dominated by finer clays and silts. So if you were to locate your turbine on a river channel, and then your next turbine is a kilometre away from that, you're going to have very different ground conditions altogether. And this just leads to, again, the complexity of a site that's on a previously glaciated terrain. So another example from here, this isn't contemporaneous by any means, but it's another example from onshore, I guess, a really nice example of an outcrop where you can see the incredible deformation that's been caused. So the above one is an example of a lithified, so much older and now compounded into rock, effectively. Example of folded and faulted bedrock. And I'm sure you can appreciate that if you were to try and drive a pile into an equivalent of that in softer sediments offshore, and then you moved a kilometre away from that, you're going to have incredibly different ground conditions. And also offshore of Norfolk, for instance, we have the interesting situation where you perhaps encounter, say, a chalk raft, which is where the ice sheet has literally plucked a block of chalk that might be the size of a car to a house from the chalk bedrock, and then transported it to an area where chalk isn't actually mapped as being a present bedrocks, and then you encounter it in your borehole. It's going to be incredibly difficult to understand these processes and why you're finding a bedrock that theoretically should not even be there. So you can really understand how messed up a site can be purely through the presence and the processes associated with glaciation and ice sheet advance and retreat. And then the bottom image is simply a smaller scale version showing you the variation. So you have these isolated sand lenses within highly deformed glacial sediments of sand, silts and clay. So it's just really, each of these units will have their own geotechnical properties and will again affect, like say, the bearing capacity and compressibility of the soil. So this all has massive impacts for your foundation design. So while I would never dream of tinkering with Charles Lyell's immortal words, I think it's useful for us, just for the remaining couple of slides, to maybe turn this phrase on its head, and instead of asking about the present and in relation to the past, we ask how understanding the past can benefit society in the present. So I don't think we need to dwell too much on this one of the final slides. The important thing here is to look at the image with the thick white line, and you can see where the ice sheet advanced in the last ice age, and the area of the UK continental shelf that's been inundated by ice. So you can see in this instance, much of the North Sea, the Irish Sea, the seas around the Hebrides and Shetlands and Orkneys, they've all been inundated by ice during this last ice age. And so we can expect to encounter highly disturbed and highly variable ground conditions associated with glacial deposits across all of these sites, really. And it's worth noting that the Round 4 and Scotland auctions recently took place. The sites are located quite significantly within these sort of areas. So I think it's a ground condition that we're going to continue to encounter going forward with offshore wind infrastructure. And this one is just an example from Dogger Bank. I want us to cast our mind back a couple of slides to Iceland and think about the features and processes we saw there. In this example here, you can see, this is like if you imagine a plan view of the site, you can see the red is a topographic high, that's an arcuate moraine. So remember the ice sheet pushing forward and bulldozing into this complex topographic high ridge. So that's there. There are sedimentary basins as well highlighted here, and these may have ponded with water, and you may get, again, these sort of glacial lacustrine type depositional basins. And all of these are draining through these black arrows with the arrowheads. These are your meltwater channels, so you're maybe infilled, again, like the glacial fluvial channels with different types of sediment. So even over one site, it's just incredibly complex how, or incredibly striking how complex the subsurface geology is and how one turbine site will vary from another. And this is just purely to give a sense of scale. I realise with COP26 I should have used Glasgow, but I'm an Edinburgher through and through, so I had to stick with it being based over Edinburgh. But it's just to give you an idea of the size, the sense of scale for the site investigations that are ongoing offshore. And I think great kudos to the entire, every member of the geo teams that are involved in every one of these projects about the type of work we do, and they do. It's incredibly challenging, and the site investigation work is takes years and years to even to come to fruition. So now that we're seeing a lot of these sites come online and we're starting to reap the benefits, I think it's incredible. It's incredibly important to acknowledge the amount of hard work that's gone into it from everyone involved. Okay, and then one of my penultimate slides really, this is an example from Dogger Bank where you basically slice into the ground and you open it up and have a look. And you'd hope, a bit like cutting into a cake, I guess, but you'd hope your cake would be like a Victoria sponge with a nice layering effect. And it's very uniform, but I'm afraid that's not the case at all. And so this penultimate slide really is just hammering home the variable ground conditions you're likely to encounter offshore. So in this example here, don't worry about what the soil units are so much, just take home that every color represents a different soil unit. And I think the important thing is not just the lateral not just the vertical variability, which is quite obvious, but also the lateral variability, because a lot of these units, due to glaciotectonic deformation, these are not continuous by any means. And so, sorry to labor the point, but where you put one turbine on your site, the ground conditions may be incredibly different from where you put the next one. And this all has to feed into your model and to do with foundation design and the geotechnical properties and basically how the soil will respond to having a foundation inserted or placed on top of it. And so this brings you back to the final slide, basically of emphasizing how geology plays a role in wind turbine generation foundation design. So you may start out your project with the majority, the idea of using the majority supported foundation, which is the monopile, but you may find that actually ground conditions aren't conducive for that. So you may look at jacket or tripod with pin piles in the corner, but perhaps your ground conditions at your site are such that you can't even drive a pile in, and you may have to consider using a totally different technology, such as a gravity-based structure. So really the subsurface is such a key important factor when it comes to managing and designing our offshore wind, that I think it's crucial that we continue to really invest a lot of time in the ground models during these projects. So yeah, that's it from me. So thanks very much, guys, and I'll stop sharing.
Thank you, Gareth. You have now heard all 4 of our speakers. We have some time to answer to your questions about the work we have presented to you today. You have already used the Q&A facility, so please continue to do so to give us your questions and indicate from whom you want a response.
Hi everyone, so there's been quite a few questions in, which is great to see. So we'll start with a few that came in earlier for Corinna. Corinna, could you please elaborate on mine water as a source of heat? Is it a byproduct of mining activity?
So the advantage of mine water is the vast amount of water that's actually within these mines, and this water sort of contains heat from geothermal sources, as well as from meteorological sources, sort of sun as well. And so pumping this heat, there's also there might be a very minor component of heat generated by reactions within the mines, but I think findings to date are such that we think that's quite not a huge amount. So the majority will come from geothermal and from solar sources. And so pumping that water through a heat pump, we can extract a certain amount of the heat, upgrade it for usable heat for heating our homes, and it really is the vastness of the resource, having access to such a large body of water, which is at the constant temperature all year round, is what makes mine water geothermal more attractive. I've actually pasted a response to that, which is maybe a bit more concise than what I've just said. So have a look at the chat.
And related to that, we had some people asking for a little bit of an explanation about how a heat pump works and the difference between heat source and heat pumps.
Air source and heat pump.
Air source, sorry.
Air source and ground source, yeah. So the heat pump really is a reverse refrigerator. We all have it. We all have a heat pump in our home in that sense. So it extracts heat from a natural source like air, water, or the ground, and then upgrades it to a higher temperature by putting it through a vapor compression cycle. And in order to do so, you need to put some electricity into the heat pump, but the heat output is actually 3 to 4 times higher than the electricity input. So while you need some electricity, you still gain more heat than, or more energy comes out as you put in. So the efficiency is 300 to 400% of these systems. And yes, and as I said, it is actually, your refrigerator works on the same principle. In terms of the difference between air source and ground source, so air source heat pumps extract heat from the air, and ground source heat pumps extract heat from the ground. The advantage of using ground source is that the ground temperature in winter is warmer than the air temperature. So you can get more heat out of the ground than you can out of the air. So the systems therefore are more efficient. The disadvantage is that you need to either sort of drill wells into the ground or install closed loops. So you need to have some sort of ground infrastructure installed to get the heat out, and therefore the systems are more expensive to install and possibly a bit more disruptive if you need to lay a coil loop or something. Although you can, because the ground is sort of warmer, you get more heat out, so you can use it for larger you can use it for ambient heat networks as well, which I don't think is possible with air source.
Thanks, Corinna. The next question is for Maxine, and that is, how many CO2 injection wells will be required to inject the CO2 emissions?
Oh, I like this question. It's very technical. So it seems a very simple question, and that's, I feel, where us as geologists can really help. So I mentioned in my presentation that it's the need to understand the character of your site, the pressure and the management of pressure. So the question is, how many CO2 injection wells will be required to inject the emissions? That is very, very site specific. So on the whole, the CO2 injection wells are roughly, the sort of industry standard is around 1 million tonnes per year. But you can only have enough injection to provided that the injectivity, the rate at which the formation can receive the gas, and that is controlled by factors such as porosity, permeability. And then you also need to have a think about the pressure response. So you're injecting CO2, it increases the pressure. What are the nature of the boundaries that that might constrain the rate at which you can inject, so, and the number of wells that you can inject? And then if you then perhaps say, well, can we manage the formation? Is it enclosed, as an enclosed formation? Has it got some linkage with the underlying strata to allow a conductivity of pressure? So each one of the formations, it'll be very specific. However, we have already thought of this, or as part of a government-sponsored project. For each one of the UK storage sites in the CO2 stored database, that has already been calculated, given the number of the rate of injection and the number of wells, and there are different tables within the database at which you can look at. It's very, very, very technical, but just as an answer to your question, as a summary, it will be very site specific. So the number of wells will be determined about the rate you can inject, the rate that the pressure is dissipated or not, and how much you can manage that pressure.
Great, thank you, Maxine. So this next question is for Gareth, and it asks, do you have any idea of the impact of floating turbines and anchoring on the costs of implementation? Although going to deeper water, would resorting to anchoring technology be cheaper than classic subsurface foundations?
Okay, right, yeah. So I don't know numbers off the top of my head for sure, but from what I understand, yeah, there could potentially be significant cost savings in floating technology. So, and it does make a lot of sense from a rational point of view, I guess, because you're driving typically a steel monopile down to 30 or 40 meters subsurface, which takes a lot of time offshore as well. So the time and costs involved in that, as well as the material costs. Whereas for floating technology, although it's an emerging it's still quite fledgling, I guess. The High Wind project being one that's up and running now. They're tending to look at more like drag embedment anchors, so anchoring systems that are we're familiar with from different technologies, but they are not looking to drive them, you know, 10s, 20s, 30, 40 meters into the seabed. So it's a very different kettle of fish altogether for material costs and installation time. The only negative, I guess, for the difference from conventional foundations is probably your length of cable that's going to be required, in terms of we're going to be much further offshore. So the export cable to get the energy back into the national grid will cost more, because it's going to be like a significantly longer cable. But no, the foundations themselves potentially be much cheaper with floating, and that's what I understand anyway.
Great, thank you, Gareth. So this next question is for Alison, and it asks, can weather have any effect on both the surface and subsurface water temperature, like in the case of the tropics and the tropical Africa, to determine the potential of geothermal energy?
That's a really interesting question. So I think, as Corinna described, there is some input from solar energy towards groundwater to be transferred into groundwater, which ultimately then becomes circulated underground, and almost in combination with the geothermal energy, depending on the depth, could be a component of that heat that we take out of the ground. So certainly in Europe, where it's cooler, we do see variations seasonally with the impact of solar radiation on the groundwater temperatures. And really, I mean, I think there's a huge amount of work to do there, and understanding how that heat is transferred through the subsurface, and how we can use it, and what the different sources of the energy are. And certainly you would imagine that in hotter countries that could be enhanced. But that's really where I think we need to start having these really extensive data sets to understand that, because there's an awful lot of complexity in how the heat and the water moves through the rocks and the shallow subsurface, to be able to give a definitive answer to that question.
Great, thank you, Alison. So we have another question here about geothermal, but directed towards Corinna this time. And that is, on the map of proposed geothermal stations, there didn't appear to be any in Scotland. The question asks, is this simply driven by targeting population centres in the first instance?
No, so I think geothermal potential exists everywhere. So ground source heat pumps can be used, you know, all across, and there's mines in the Midland Valley of Scotland which are also feasible for ground source heat pumps. You know, for mine water geothermal, which use a heat pump. But the deeper geothermal targets are more dependent on the geology. There are targets in Scotland, including some sort of radiogenic granites, as well as some sandstones. So the maps I've shown, I'm not entirely sure what you refer to when you say stations. I wasn't aware I'd shown that. But there is targets there, like, but they're more sort of dependent on the geology than perhaps the ground source heat pump systems are.
Just to follow up on that, Corinna, I think the question was maybe asking if there was a particular reason, albeit geological or policy-wise, why Scotland would have less or more than other countries in the UK. To your knowledge, is there any, other than the geology, is there any factors on the adoption through policymakers with geothermal energy at this stage?
I think the Scotland has its own. So this is a devolved matter. So how geothermal energy to a degree, and so Scotland has its own policy. So if anything, I would say Scotland is more supportive of the geothermal energy. Has certainly provided more funding for it to be explored compared to England and Wales. So if anything, I do think Scotland is ahead of the game on geothermal.
Brilliant. Thank you, Corinna. So the next question is for Maxine. And the question asks is whether or not we have enough information from the Norwegian Sleipner project. Is any data publicly available? Thank you.
So the Norwegian Sleipner project is a fully commercial project. It was initially implemented to capture CO2. It's not from CO2 from industry. It's CO2 that would have been emitted from produced hydrocarbons. And that was done purely, it's a purely industry project because the Norwegians do not permit emission of CO2 along with their hydrocarbons. And this is when it was implemented in 1996. So it's solely a commercial project. Initially, it was by, the company was called Statoil, it's now called Equinor. But once it started, you can imagine it was a very, very exciting prospect. And research organisations like our good selves, the British Geological Survey, were very keen to use that as an example and to measure and to monitor and do as much research as we can. And there is a lot of information available from Sleipner project. One of the very interesting things which is seen very, very often is the monitoring data of the gradual migration of the injected CO2 since 1996. And that work, there was work, EC funded work that was done by my own colleagues, including Chadwick and Williams, and they have interpreted the results of the data that was released from the Sleipner project. I think there were many EU projects centered around Sleipner, so that is publicly available, and I believe that Equinor still allow access to the images and some of the findings from their commercial project at Sleipner. They also have another one at Snøhvit, which has been operating, so Snøhvit, that has been operated in the 2020s, and they're now about to start their third project, which is called Longship. And there is a lot of information available on sort of Snøhvit and on Sleipner that has been used for research purposes. I'm not so sure that it's publicly available. I think that would be part of a research project, I think, Inquirer.
Great, thank you, Maxine. So we've got another question here for Gareth, and that is the foundation only a concern for wind turbines as opposed to oil and gas well conductors because we have more hydraulic capability with a drilling rig?
Okay, I mean, I don't have a huge amount of experience with foundation for oil and gas infrastructure, I guess, but I think it's probably worth flagging that although a lot of knowledge, a huge amount of knowledge has come over from oil and gas into the renewable sector, which is greatly appreciated by everyone. Some of the foundation designs are slightly different, I guess, because there's different pressures and loading, perhaps on the different types of structures involved. So, I mean, cyclic loading from effectively the shaking of the turbine itself through the met-ocean conditions, so wave loading and the vibrations caused by the turbines turning and things. These can have significant consequences, I guess, for the foundation design for a turbine, which maybe don't have to be considered to the same extent for oil and gas infrastructure. And oil and gas relies or has classically relied a bit more on gravity-based type structures, which are much larger concrete-based structures. So different ground conditions for different, or same ground conditions, but for different infrastructure. I guess there'll still be a consideration for both industries, I guess. Although I'd probably say that offshore, it may be more of a consideration, I'd say, for offshore wind. Although I'm sure that somebody will disagree with me on that. But yeah.
Great, thank you, Gareth. Okay, we've got another question here for Alison this time. In a geothermal context, mine water temperature is about 25 degrees C. Is that simply due to the depth?
So yeah, the geothermal gradient as we go down deeper increases, and so mine workings that are deeper are generally hotter. A lot of the mine workings in the UK that we might use for mine water heat do vary between about 12 and 20 degrees C, but obviously in some places they are hotter. We've actually mapped those temperatures out. So work between the Coal Authority and the Geological Survey has produced a series of maps at different depths that cover all of the coalfields of the UK, where you can look at the temperatures that are at different depths and have a look at those temperature resources if you're particularly interested in that.
Thanks, Alison. The next question I can actually answer, so I'll give the speakers a quick break. And a few people are asking if the slides and presentations will be made available after the lecture finished broadcasting. And the answer to that is yes, we are recording this presentation and we'll make it available through our website and email link to those that are registered in the coming days. And then the next question is posed to two of our speakers, so to Corinna and Maxine. The UK government seems primarily interested in investing in blue hydrogen at present and largely seems to have forgotten about geothermal. How do you think it is best to encourage the government to invest in geothermal as well as hydrogen and CCUS? Max, I don't know, do you want to go first and then?
Okay, yes, I'll answer just very, very quickly. First of all, inquirer, we have to do everything. I appreciate that we will not reach our net zero emissions target unless we do everything. And that's not just a technology, but our behaviours as well, and our usage and our increase of efficiency. I'm sorry, this is very important. You know, it's not just something that somebody else does that makes it easy for you. No, everybody's got to do everything, including emissions capture, including converting our fuels, and also including geothermal heating. Yes, there is a recent interest in what's called blue hydrogen, which is hydrogen by reformation with CCS, as in my talk. But really, the need is to be able to reduce our emissions, and we can do this very quickly. One of the things is that Corinna mentioned is that if you want ground source heat pump, you have to have infrastructure associated with a building or cluster of buildings. With I think the enthusiasm for hydrogen and CCS is because it means we can convert everybody's house and everybody's boiler and everybody's cooker, and so on and so on. So it's rather than having single source, you know, many tiny little sources, we can capture it at source, so to speak, before it goes to your house. So there's an immediate big hit. However, there is a limit to everything that you can do, and so with one technology, and so we have to use all technologies. And it may be that the hydrogen use of hydrogen instead of natural gas may not be suitable for a house, or it may be more suitable for it to have geothermal subsurface heating. So I don't want to say that CCS and hydrogen is better than geothermal. We need to do it all, and it is as appropriate for whatever particular setting. Corinna.
Yes, so I certainly I recognize in the question, and like I see in the question and recognition that certain technologies are perhaps talked about more, while others might not be recognized as much. And I would fully agree with that on the geothermal side. And the question, I think, is what to do about it. So this is part, and Maxine mentioned that I have a academic placement at the Parliamentary Office of Science and Technology, and the aim of that is to provide a what they call post brief for MPs that actually informs about the geothermal potential of the UK, advantages, disadvantages, and so gives a objective picture of what the technology can do. So that is one way of sort of raising awareness. And I mean, the good news is there has recently been a Westminster Hall debate, which is available online on geothermal opportunities. So my hope is that awareness is increasing. But I'd agree with Maxine, like, it cannot be one technology. Geothermal isn't going to solve our decarbonisation problems, but it is one player in a bigger pot of technologies.
Thank you both. So we have a question here for Corinna again. Now, in your talk, you mentioned that geothermal energy has the potential to power up to 15 million homes in the UK. Now, this may be a difficult one, but the question asks if you're able to give an indication of how many power plants would be required to reach this figure, and what sort of timescale providing power for 15 million homes through geothermal is likely to be viable on.
So I don't have the number at the top of my head. I think sort of a coal power station, a large coal power station has got a 200 megawatts capacity, and a sort of a sort of large, or like a nuclear power station. I think it's, yeah, I can't remember which one is about 1,000. So I think you'll have to, I'm afraid, do the math yourself. I don't have it here. In terms of the time frame, these systems have been, so in other countries, so we have one system that's operational in the south of England, in Southampton, which has been chugging along for about 30 years. So they are, that is the lifespan of the system and more. So we'll have systems like that in other countries. So I do think 30 years, 40 years, 50 years is realistic for a geothermal power plant. In theory, if you use your resource sustainably, you shouldn't have, there shouldn't be a limit. It might just be sort of that the actual technology needs to be updated. But yeah.
Great, thanks, Corinna. I think that was a tricky question. Okay, moving on to this next one. This one's for Alison. Geothermal and wind-driven measures to decarbonise humanity all require an investment of carbon for planning, construction, operation, and decommissioning. Do we have a clear understanding of the balance points when carbon is saved and there is a return on carbon investment?
So, translating that question, I think you're asking, is the amount of carbon that we use to construct the operational aspects of these systems greater than the amount of carbon that we save? And I think that's an area where people are looking at what they would call life cycle assessments for CO2 used in these processes to assess exactly these kinds of questions. But we need schemes like Corinna's just described that have been running for their operational lifetime to really understand the answer to that question, because if it's a new technology and we don't know how sustainable it is and how long it's going to last, we can't realistically do those kind of life cycle assessments. So it's really important we get the evidence and the data to make realistic assessments of what goes in and what we get out. And I would be interested to really possibly ask the other panelists, Gareth and Max, if those kind of calculations had been made for wind and CO2, because they're a little bit more mature, those technologies. Max is nodding. So I was wondering if I could pass that and broaden it a little bit to them.
So that's very familiar terminology to me, Alison, because the sort of the methods that you use to capture CO2, to transport and to store it, you do have to be very careful that what you're doing has a significant and net decrease in terms of CO2 emissions. So life cycle analysis is very important, and the objective is to make it as efficient as possible. There has to be a significant net gain for a project to be considered, as a sort of an emissions reduction technology.
I don't know from wind. I have to be totally honest. I don't know quite the offset, or at what point you're producing, you're saving more carbon than you are than you've used initially. Because I mean, it's a good recognition, I guess, that to produce these steel monopiles, for instance, will have an implication, and where you produce them and geographically, because they have to be shipped to site, that all has a carbon footprint associated with it. So it is a fair question, a fair point. I guess one answer to consider as well is the fact that we also have to do similar offset or similar investment in infrastructure for traditional energy sources too, that will still have a larger carbon footprint during when the fuel is used. So I guess in some ways, there's the offsets, hopefully much more positive with other renewable technologies. And eventually there will be an offset where you'll be saving, obviously, carbon as opposed to just continually producing.
I think one of the things about using is if you can try and use infrastructure that you already have. And so, you know, the hydrogen production with CCS, you are still using all the same pipes. For the most part, almost all of your cooker and almost all of your boiler. And for CO2, where it is offshore, we're able to reuse, in some cases, the offshore infrastructure, the pipelines, and to some extent the wells. So then that cuts down on the new emissions that you would have to discount as part of implementing a project. So all of these factors are weighed up when you're considering a life cycle assessment of your CO2.
Thank you, everyone. So we'll try and squeeze in just one or two more questions before we run out of time. So this next question is for Max. When CO2 is injected, will it have associated water and other contaminants? If so, is there potential to alter the mineralogy of the receiving sediments?
Okay, so CO2 that is injected is pure CO2, like 99.99% CO2. The objective is to reduce the impurities and also particularly the water, and this is to preserve the infrastructure. So if you have water and carbon dioxide makes carbonic acid, and therefore you need to make sure that there is no acid corrosion for your infrastructure. So that's the first part of your question. So it is virtually pure CO2. Does it alter the mineralogy of the receiving sediments? So first of all, the CO2, you probably know from whatever fizzy drink you like to drink, whether that's a cola or tonic water or champagne, that the CO2 dissolves in water. And so, in fact, it doesn't necessarily attack the sediments, but it does, when it becomes very saturated, it will start to precipitate as a carbonate mineral. So this enhances the CO2 storage, not in gaseous form or liquid form, but also in solid form. And of course, there are concerns about contaminants, and this is parts of the work of many geochemists over decades to invest this since the start of CO2 injection, for example, of the projects we saw earlier. So there has been plenty of investigation to make sure that the contaminants are not harmful, and also is that the mineralogy is being used to actually enhance the capture and very permanent storage of CO2 as a carbonate mineral.
Lovely, thank you, Maxine. We've still got quite a lot of questions that are open, and I don't think we're going to have time to answer them all. So I think what we'll do is we'll take these offline and we'll include a question and answer sheet when we send out an email with a link to the recording. But if I may, there's just one final question, if we can sneak this one in, and that's for Alison and Corinna. And that asks, why go to the effort and cost of drilling a deep well rather than using flooded mines that are already in place?
Can I answer that, Corinna? So obviously the mines that we're using are there and they're flooded. I think the question is maybe alluding to existing discharges from mines and also existing pumping stations from mine workings. And certainly that's very much something that the Coal Authority is looking at. So they maintain the UK's mining heritage and coal mining heritage, and there are a number of existing pumping stations where the heat is being looked at to be utilised where it's already pumped, and similarly where there are natural discharges, those are also areas where people can look at using the heat that come from those. So those are being looked at, but they're not always in the right place where the demand is. So if you have one, great. If you don't, then you might have to drill a borehole.
Could I just add to that? It's also a question, so there's that geographical element that Alison has described, but there's also a question of scale of how much heat you require. The mine water geothermal requires a heat pump and sort of is feasible for maybe a few hundreds of homes if you drill a deep well and you have a good source, you may be able to provide tens of thousands of homes with heat. And a good example of that is Munich, where they use a geothermal resource for supplying heat to large heat networks within the city.
Okay, so thank you. I would like to thank our speakers. So that's Gareth, Alison, Corinna, and also to thank you for your attention and your listening through all the way through an hour's worth of lecture and all of your very, very interesting questions. As JP has said, we will try to respond to your questions and paste them on the BGS website, where there will be a copy of the recording of the proceedings available to you. So thank you very much for your interest in the BGS and our presentations ahead of the COP26 conference in November. So thank you very much and goodbye from us all.